Let me know if you all can see this.
Yes, we can.
Okay. I'll actually straight away start with the presentation today because it is going to take some time. I am going to cover a lot more than before, and it would take some time. So I will spend the next week or so, or if I have some time left, I will spend that time with the assignment, as I want to start with this presentation today straight away, because it is going to take some time to actually learn this topic. So if I have time in the end, I will definitely cover the assignment. I know you all have got slightly confused with the grid search CV and k-fold cross validation, but yes, I will cover them, but I would like to get on with this topic first today, as it's there's a lot to cover today, so that's why I wanted to start with this. So okay, if you all are fine with that, I'll get started. So let's like today, this is what we're going to cover. We are going to mostly talk about neural networks. It's There's no difference between deep learning and neural networks. It's the same thing. It's just another fancier name for neural networks. So artificial neural networks has been there for, I don't know, so many years. Actually, it's not something that's been recently invented. The concept of artificial neural networks has been there for, I don't know, like 20, 30 years or something. Like, it's been there for a very long time, but recently it's been very exciting and very powerful and actually working very well because of GPUs, because of our computing power, and because of the fact that our computing power has actually increased, and it has become cheaper to buy uh, uh, good quality, basically the electronic chips and the GPUs, and the computational power has increased as compared to before 2000s. So in the before 1990s and 1980s. So that's one reason that deep learning and neural network has become very popular. So the algorithms, uh, uh, that I'm going to explain today have actually been there for a long time, and that's what we're going to cover. So the math behind neural networks, and then different types of neural networks, and then we look into something called recurrent neural networks, where you can actually use them, and then lastly we look at convolutional neural networks, and then we'll start our notebook. So I have uploaded the notebook and the presentation onto the Google Drive, so you can download it. I will upload the notebook once more because I have to do lots of hand calculations today to actually explain it better. So you will see few slides empty. You won't see anything on the slides. If you want, you can download them right now, or you can wait for me to actually finish the session to re-upload the notebook, so the presentation. So once again, right now the notebook and the presentation have been uploaded. So, okay, let's start with neural networks. What are they? So basically, neural networks are nothing but they are a class of machine learning algorithms. So basically, they are a class of machine learning algorithms, and then they have been inspired from trying to mimic our human brain. So we have neurons inside our brains that actually fire off whenever we want to uh, analyze something. Like, let's say I'm actually speaking right now. So many millions and millions of neurons are actually firing in my brain right now, to help me comprehend, or to help me speak, to help me visualize my laptop and my phone and my pen, and all those things are actually happening right now in my brain. I can't go too deep into it because I'm not that aware of the subject, but on a basic level, the idea was to mimic how we actually as humans actually learn something. So that was the entire one origin, one like uh, one kind of an origin for where neural networks actually came from. So it is still a machine learning algorithm. The idea is the same. There's nothing different. You have an input, you have your model, you pass the input data into the model, it trains it, and then you get some output. The idea is exactly the same. It's just that there are huge computations involved in this part. So where the data is fed into the neural network, there are huge matrix multiplications and very highly complex computations are taken place inside the neural network. And then the neural network learns weights. So basically, if you remember linear regression, the beta 0, beta 1, and beta 2, those are weights or coefficients. So those weights are actually what represents the model. That's what defines the model. So those weights are learned based on the data and based on the output. The entire concept is still the same. It's just that these are a whole bunch of different class of machine learning algorithms. The meme is just a funny meme to show why it takes so much time to actually train machine learning neural networks, because basically the guy is sitting and he's waiting for his neural network to train, and he turns into a skeleton, because if you see, it actually takes a lot of time, because there are so many parameters inside a neural network that to train them to adjust the weights so that you get the right output, that process actually takes a lot of time. And that's what this meme is showing you. And if you find it funny, okay. If you didn't find it, it's a bad joke, then let's move on. So okay, let's actually try to cover some terminology today. So before we actually get into how a neural network actually works, we have to understand few things, as these are the things that I will keep saying continuously for anything. And these are the most important terms that keep coming up in any kind of neural network that you're going to see ever. So to start with, the first thing is neural network. So neural network, as I said, is a machine learning algorithm, and it's still the same machine learning algorithm that takes the input and then does some computation and then gives you an output, some prediction. And then it learns to adjust its weights, the coefficients or the weights inside the model. And based on those weights are nothing but they are just numbers. Weights are nothing but numbers. Those numbers are multiplied with the input to get some output. In a very simple terms, that's what happens. It's just a matrix. You have another matrix of input. You just multiply your input to this whole set of weights, and then you get your prediction. That's all machine learning is all about. Now, neuron is nothing but a single unit inside this entire neural network. So if you've already seen the image of a neural network, you would see it drawn as circles. So there will be a bunch of nodes inside the neural network. So each of those nodes is nothing but a single neuron. It's a single unit that actually performs this computation. And then there are weights. So as I said, like linear regression, weights are nothing but those beta coefficients. Here we refer to them as W. So weights are nothing but the weight defines the model. So weights are nothing but a bunch of numbers that actually define your model, and then the model relies on these numbers to actually get its predictions. And then there are layers. Now layers are nothing. Now that you understood neurons, layers are nothing but a stack of neurons. So layers are nothing but neurons stacked together one by one. So all this will become much more clear when I actually show you the picture. But otherwise, a layer is nothing but a stack of neurons, and then there are multiple layers within a neural network, and that's where the term deep learning actually comes from. So as you have more and more layers, it becomes deeper and deeper, and that is what we mean by deep neural network. So the word deep actually comes from the fact that you have stacked neurons as a single layer, and then you have stacked multiple layers side by side. All this thing might be a bit difficult to imagine, but it will become clear when I show you some examples. Then we have input layer. So input layer, so some papers consider input as a layer, some don't. So I would say you can stick to anything. Otherwise, the only difference is in counting the number of layers. So input layer is nothing but the input data points. So whenever I say layer, a layer is nothing but something that has some computations and some update on its weights. There's nothing going to happen in the input. So input layer is just a placeholder to hold the inputs. So what I mean by input is, in your Titanic dataset, each row. So each row is considered one input. So if you want to consider it as a layer, you can, but otherwise, in general, a layer is referred to the stack of neurons where the actual computation happens and where there are weights. An input layer has nothing to do with computations. It's just a layer that holds the data and it's being pushed forward. So that's why I refer, it's a bit ambiguous to say whether it's a layer or not. And then there are activation functions. So activation function is a nonlinear function. So if you remember logistic regression, if you actually remember what we did in logistic regression, we had a sigmoid function. So that is what is commonly used in neural networks. So an activation function is nothing but I said that inside a neuron, there is some computation that takes place. Now, activation function is one part of that computation. So what happens is, inside this neuron, there is an activation function. Consider, let's say, for example, the activation function is a sigmoid function. If you remember the formula for a sigmoid function is 1 by 1 plus e power minus x. So the data is passed into this through the huge network, and then once you get the output is actually passed through an activation function. The purpose of adding the activation function is to provide nonlinearity. It will, so I'm actually going to draw it in the next slide, or else the purpose of activation function is to provide some kind of nonlinearity to the entire neural network. Let's say there are no activation functions. A neural network is almost same as a linear regression. So I told you there are weights and there's an input, and the input gets multiplied by the weights. This sounds similar to linear regression. I have weights beta 1, beta 2, beta 3. I have input x1, x2, x3. All I'm doing is I'm multiplying both of them. So then what's the difference between a neural network and linear regression? This activation function is the difference. So the activation function actually adds a layer of nonlinearity so that the neural network can actually model very complex functions. So I will draw that and show you, and that will become much clearer. I guess there are a few questions. Okay. Okay. So now activation function is there everywhere. So activation function is there throughout all the neurons. So as I said, just repeating it once more, activation layer is meant to add nonlinearity to the entire neural network architecture. And how does it add it? We look at when I actually do the computations. Now, epochs. So this is another common hyperparameter that is actually what it actually means is one epoch is actually equal to passing the entire data set through the neural network once. So once again, one epoch means you actually take the entire data set and pass it through the neural network, and then training takes place. So one epoch is basically the entire cycle of passing the data through the neural network, doing the computations, getting your output, getting your loss function, training the weights, and again repeat it. So this whole cycle of input to output and then repeat is one epoch. This is a hyperparameter, and then the way that people tune these hyperparameters, as you keep training, if you feed the model more and more data, it will actually learn more and more. And if you start training it for 100, 200, 1,000, 10,000 epochs, it learns more and more. But there is a limit until where you can actually go. And then lastly, batch size. So whenever we train, and batch size doesn't necessarily, so batch size refers to splitting the entire data into pieces and then sending it. This is not related to training and test split. That's different. Batch size means if you have, let's say, 1,000 data points, I'm going to feed 200 data points in batches to my neural network. So I'm going to feed the training is going to take place in batches. So I'm going to feed 200 data points at once to the neural network. Training is going to take place batch wise. That's what I mean. That's what this batch size represents. So the number, if the batch size is 128, that means I'm feeding 128 data points I'm broken the entire data set into 128 buckets, or basically 128 individual chunks, and then I'm feeding them batch wise. That's what this batch size actually represents. So whenever I refer to data points, data point is nothing but one row in your data, and features are nothing but the columns. So okay, now I guess there are questions of activation function is applied to each neuron. Yes, I'm actually going to show it to you now how activation function is actually being applied, and then you will get a clearer picture. So okay, it's time to draw now. So now I was talking about the nonlinearity. So why do we need neural networks? So okay, so if okay, so consider a simple like a single feature, like just a data, like a data with like single feature, like let's say this is the my data points are scattered in this way. So for like let's say this is x and this is y. So let's say these are my data points. I have circles here, 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 here. Okay, these are circles actually. Okay, I have circles, and then now I have let's say squares. So squares. Okay, now can anyone tell me which model I can use here? How do I separate these two? There's a simple model that you actually just learned, and can you tell me where is the decision boundary? Like what separates these two classes, and which model can I use here? Yeah, linear regression. You can use decision tree, but the simplest model is linear regression. The reason I'm saying linear regression is because there is a line that a linear line, a line that actually separates this data. So this data is actually linearly separable. By linearly separable, I mean there is a single line that actually clearly separates this data. So always prefer the simplest model first. So like what I just said is actually called Occam's razor. I think some of you might have heard of it. It has nothing to do with machine learning. It is from a philosopher. Like there was a philosopher, I think his name is William Occam. He proposed a philosophy saying that I mean it got translated and misinterpreted in many ways, and then finally what it actually means is if you have a simple solution, just go for it. That's the most layman term of explaining that philosophical idea, but it's much more complex than that. Why I'm saying that is because here the clear solution is that there is a linear line that clearly separates this two data points, and then I can use linear regression, and then sorry, not linear regression, logistic regression. I can use logistic regression to actually clearly classify these two data points. So since this is a classification task, it's not a linear regression, it's logistic regression. So logistic regression will give me this decision boundary. So this is the decision boundary. Now let's look at another. Now that you understood this, let me show you something else. So okay, let me just remove this. Okay, now imagine I have those circles and squares, but this time imagine that it's something like this. So okay, imagine that the squares are here, and then there's a circle here, and then there are squares here, and then there's a circle here. So somehow, where is my decision boundary now? So somehow my, like, this is where it is getting separated, like it's something like this. Like, I mean, how do we even model this? Like, what is the, okay, can anyone tell me what is the equation for this straight away? Is there a straight away answer? What is the equation representing this line? Without just thinking, can you tell me what is the equation representing this line? You don't need to do any calculations. Obviously, it's very difficult to get that. Like, I mean, I can't even imagine what kind of it is a nonlinear equation, but we don't know exactly what is the equation of this one. Like, if I give you a graph and I give you a straight line, I can clearly say that this is y equal to x. I can clearly get an equation, but what is the equation of this line? How do I even model this? Now, here is where the nonlinearity, the activation function, the nonlinearity of neural network kicks in. So because there are such data points where there is high nonlinearity, decision trees can work here. There are other nonlinear algorithms that can work, but neural network is one such algorithm that actually very nicely approximates this function. So neural networks can also be called universal function approximators. Estimators. So what I mean by universal function estimators is, you give it any distribution of data points, it will learn the because of such high nonlinearity present inside the neural networks, it will actually learn to model this exact decision boundary, and then it will make its predictions. So when I say neural network trains its weights, when I say neural network learns something, this is what it's actually learning. It's learning to separate, it's learning this function. It is so nonlinear, and this is the reason that, let's say I have let's say I use let's say I actually use this one. Let's say I use linear regression, sorry, logistic regression. At most, what it's going to give me, it's going to give me some line, I guess something like this. What about all these data points? They are all misclassified. These are correct, these are also correct, but what about these things? These are all misclassified. So linear regression by its own cannot do this job of separating it well enough. That's where actually neural network comes in and helps us to get that stuff. So Evan mentioned kernel trick. That is a good answer actually. So I haven't talked about it. There is something called kernel trick. I won't derail this topic too much, but essentially, without neural networks, one way to actually solve this is to map this entire thing to a higher dimension. So let's say this is 2D. Let's say I take it to 3D. Now imagine that in the 3D space, this is where they are scattered. Imagine that in the 3D space, there is a linear line, that linear hyperplane that actually separates the data points very well. Now I can still apply logistic regression, but in a higher dimension. So that's just to complete the answer that Evan mentioned. Otherwise, neural networks helps us get this kind of a nonlinearity. So this line that I just drew here, so it's not possible to do logistic regression and get this one. I hope that's clear. Now we'll actually look at the computation. So I've been talking about computation and activation function and neuron and so many things. Now let's actually do one computation and see how it actually works. Okay, so now, so this is a single neuron. Let me change the pen back to blue. Okay, so this is a single neuron. So this is actually a single neuron. Okay, so now these are your inputs. So if you see these ones here, these are your inputs. By inputs, I mean thinking in terms of the Titanic data set. So x1 here can be age, and then x2 here can be fair. x3, what's the other feature? I guess embarked. So this is what I mean by input data point. So each so x1, x2, x3 are nothing but the values of each individual feature. And then this one is a bias term. This is just, so this B is equivalent to, so I'm again going to show the example of a straight line. So the equation of a straight line is y equal to mx plus c. So this c is nothing but the intercept. So it's the bias term. That's what this one here represents. So now how do we, now what is this y? So y is finally our actual output. So this is nothing but our output. This can be a classification. If it is a classification, it's 1 or 0. If it is a regression, then you get the space of all real values. So I guess, yeah, R. So sorry. So 1 minute. Okay. If it is regression, it is basically the space of all real values, and if it is classification, it's just 1 or 0. So that is what essentially this single neuron computes. So it takes in the input, it does some computations, and then it gives output. Now, what does it actually do inside? Let's look at that. So the way that these things are going to be combined. Okay. So the way that these things are going to be combined is, it's just going to be multiplied. It's just like the linear regression example that you've seen. So what's going to happen is, I'm going to call the let me call this A. So A is just representing the first step of the computation. So what's going to happen is, each one is going to be multiplied. So it's going to be x1 w01 x2. It's exactly like linear regression and logistic regression. x3 w03 plus b. So this is what is, let's call it A1. Let's call the first step of the computation A1. Now this notation, okay, I am using this notation. There is no universal notation. It really depends on you. But what I am going to say is, this 0 is just the fact that there's only one neuron, and there's only, consider this as a single layer. So there's only one layer, and there's only like there's only one layer here, and that's the output layer and nothing else. So and the 0, I'm indicating 0 as the layer number, and then 1 for just the position of that output. So this is just my notation. There's no universal notation. So okay, we did the first step. We got A1 as this one. Now where does this activation function come? So the activation function is actually going to come here. So the next step is to actually apply sigmoid of this A1. So what happens is, you get 1 by 1 plus e power minus A1, and you get some output, some set of numbers. Now this y output is nothing but this A2. So this is what happens here. So basically, you got all the inputs, you multiply it with their weights, and then this is the nonlinearity. So this part, so this is where the nonlinearity happens. So, and this is the activation function. So the activation function. Okay. So I hope this is clear. So this is what happens. Like basically, this is what happens inside inside a single neuron, inside a single unit of the entire neural network. So once again, quickly going over it. The first step is to just multiply the inputs with their weights. Now, and then once you get that, your next step is to apply the sigmoid function, and the last step is the sigmoid is the answer and nothing else. Let's say this is the classification task. Sigmoid will give you a value between 0 and 1, and I am going to decide that if the sigmoid value is greater than 0.5, my class is 1. If it's less than 0.5, class is 0. If that happens, that's it. I got my classification 1 or 0. So this is essentially what happens, and this is, I'm going to show you next. This step, what I just did, this is actually called forward propagation. So this is one step. This is one forward propagation, one step. Now, where is the training? Okay, now that I predicted my output, I don't even know whether it's correct or not. Where does the training take place? No, the training happens for these things. So these are the weights of the neural network. So these are the actual weights of the neural network. And then these are the ones that are actually trained. So these are the ones that are actually trained. And then once the model learns what is right or wrong, the weights are actually adjusted, and then they're adjusted in a way to get the ideal output that you actually want. So this is what happens inside a single neuron. Okay, I see there are a bunch of questions. I will take them. Yeah, most of the questions. Okay, so most of the questions are about what is the purpose of that B, how are W01, W02 determined, and then can you explain this whole thing again? Okay, I see. That sums everything up. So, okay, so I'll start with B. So B is nothing but it's not to avoid bias. It is the bias term. So what I mean by bias term is it is equivalent to this thing over here, this C over here. It's equivalent to this C over here. Why do we have this C? This is just a intercept. So apart from your weights, we also have a bias term to further maybe fine tune the weights, fine tune the predictions even more than what the weights can provide. It's called a bias term. It has nothing to do with the model's bias. That's actually very different. It's equivalent to that C. So I hope that B is clear. And then since we only need B, that's why we are multiplying it with 1. It's just that, okay, this is actually equivalent to 1 multiplied by B. That's the only reason I have 1 over here. It's just to add that bias term. So what happened in this computation is initially after a simple multiplication takes place, A2 is nothing but sigmoid of A1. So it is just that this entire thing, this entire A1 is taken and it is fed inside this sigmoid function. And then the result is that I'm just going to apply the sigmoid function to this entire expression. So let's say I got some value over here. Let's say I got 0.567 something. Now A2 is nothing but sigmoid of this one. So it's 1 by 1 plus e power minus 0.567. And whatever that value is written here. That's all A2 is, and that's the output. That's what sigmoid is. I hope, Masha, that is clear. Now, last question is, how is that W01, W02 determined? So we don't have anything to start with initially. Like it's totally blank. Like there is no W01, 02, 03. So we initialize it randomly. We actually just randomly initialize W01, 02, 03 to any value. And then I haven't explained it yet, but there is an algorithm called backpropagation that actually helps train the weights. And the reason that I put the message in the group saying that you need to understand partial derivatives is precisely for that. So W01, W02 are initially, they are random. So they're randomly initialized. I'll try to write it as neat as possible because you all have to understand it again. Okay, so these are randomly initialized, and then once they are randomly initialized with the backpropagation algorithm, there is something happen. I'll explain it later, but basically the backpropagation algorithm will make sure to update W based on my predictions. Let's say initially I predicted 1, but the answer is 0. Okay, update the weights. Next time, let's say I predicted 1 and the answer is 1. That's correct. Update the weights again. Let's say I predicted a mistake. Update the weights again. That's what happens essentially in backpropagation algorithm. It trains itself. Yes, exactly. So this is what happens in all the machine learning algorithms. Like people are looking at neural networks as some magic, but essentially it's exactly the same concept. You have some weights, you have your output, there is a loss function, you train the model, and then the weights are adjusted. The exact same step happens in all the machine learning algorithms. It's just that because of such high complexity, neural networks can model complex functions much better than normal algorithms. But this is not always a solution. as I showed you, sometimes the simpler things are the best ones. Okay, so now that we understand, a single neuron, so let's actually look at a two-layer neural network. Before I go into this, how many of you have heard of the word perceptron in this context somewhere? So I think some of you might have heard of something called perceptron. So a perceptron is nothing but a single layer neural network. So you might keep hearing this term in the context of neural networks, but essentially a perceptron is nothing but a single layer neural network. This is not a perceptron. Here we have two layers. So two layers of computations are taking place. If let's say I didn't have this, okay, let's say I actually didn't even have this entire middle layer. Let's say this is not there. I only have this one and I have my output. That's a perceptron. It's just a single layer. So I think the previous example that I showed, this can be, there's only one layer here. This can be considered this is a single neuron, but this can be considered a perceptron. So you might have heard the term multi-layer perceptron. So that is actually what a neural network is. Multi-layer perceptron. Perceptron is a single layer. When you stack multiple layers together, that's called a neural network. That is a multi-layer perceptron. So all these things are actually referring to the same thing. So perceptron is a single layer. Multi-layer perceptron is just stacking single layers, and then together it's just the artificial neural network. So it's important to get these terms out of the way right now, because there are so many terms being thrown around that people get confused. So let me remove this. Okay. So now, okay. So now this is the actual. Okay, this is the actual two-layer neural network. So what happens here is, I have actually specifically, before I proceed, I have actually specifically chosen red, green, and blue for one purpose. If any of you can figure it out, that's great. But I've actually chosen these as a joke, not as a joke, but as a continuation to what I'm going to show in the end. But otherwise, these colors are not randomly chosen. So now, as you see, as I said before, this is now, so if you remember this image from before, this is a single neuron. Now a stack of neurons and then combined with multiple layers. Now this is how an actual neural network looks like. So now the way computations happen is exactly as happened before. So try to pay attention here. If you feel a bit sleepy in the later part of the slides, that's okay. But this is the most important part that you have to understand, because once you understand these concepts, everything else is exactly the same thing. Now, if you look at, so yeah, I guess you all have really understood why I chose red, green, blue. RGB is the how we perceive things. So okay, so now that we have multiple neurons stacked together, and we have a hidden layer, and we have an input, and we have an output, the way computations take place is again the same thing. So we have weight over here. So we have a W. Okay, since this is the hidden layer, let's say it's layer number 1, and then weight number 1, and then layer number 1, weight number 2. So like this is for like, and then where is the other one? Okay, sorry, this is 3, and then there's W1, 2. And same way, there are weights for these green arrows as well. So let me clearly change the color so that it's very easy to understand. And then there is a W, let's call it maybe 2. And then there's 1, W2, 2, and then there's W3, 3. I'm not talking about the layer. I'm actually talking about the input here. So let's not confuse ourselves with the analogy. So sorry, with the notation. For now, let's consider 1, 1 actually means input number 1, and then the first weight, and then input number 1, second weight, input number 3, third weight, input number 2, weight number 1, input number 2, weight number 2, and then input number 3, input number 2, weight number 3. I wrote the wrong one here. This is 2, 3. Okay. And then similarly, there will be weights over here as well. So for the last one, which is the red weights, So let's say this is 3, 1, 3, 2, and then this is 3, 3. So now that we have those weights, assume that for now, let me go back to some other thing. Okay, let me use black. Okay, so now assume that we have sigmoid functions here, here, and then here. So now what happens in, and then again assume that there's a sigmoid here. So now what happens is there are weights here as well again. So W, let's say 1, W2, and then W3. So everywhere there is a computation, that's called a layer. So if you notice, I'm actually not writing any W's here. Why? Because there is no computation happening. It's just the input is being fed into here. So this is just the like you can say ingest the data. So you don't need to get confused here. It's just that the data is being fed like this. So it's just a placeholder. That's all. So the data is being fed, and from here, the computations are actually taking place from here. So from this stage until this step, this is where the computations are actually taking place. Nothing is happening previously, only from here. Now, remember what I showed before. A1 is x1 W01, x2 W02, x3 W3, so on. The exact same thing will happen here. So this one, what happens here is these three are combined with these three weights. Now you see here, x1 is actually multiplied with W1, x2 is multiplied with this, and then x3 is multiplied with this line. And then again, x1 is for this is the first, this is the, let's call it, so this is the hidden layer 1, hidden neuron 1, this is the hidden neuron 2, then hidden neuron 3. So H1 is nothing but a function of x1, x2, x3, and then W11, W21, and then W21, okay, 33, yeah, W33. So H1 is nothing but a function of this one. What I mean by function of is nothing but it's just multiplied. So the result is what happens here is it's just H1 is nothing. Okay, sorry. I hope I'm not confusing you. Try to follow along with me. H1 is nothing but sigmoid of x1 times W11 plus x2 times, now which is the weight here? W21. So W21 plus, where is the weight for x3? It's W33. So x3 times W33. Now this value is what is going to come here actually. That's what's going to happen. All these are going to be combined in this way. Similarly, H2 is going to be a combination of x1, x2, x3. H3 is going to be a combination of again x1, x2, x3. Now, how many parameters are actually there here? Can anyone tell me how many parameters do we have just in this part? Just in the first, the colorful arrow. How many parameters do I actually have? Can anyone guess? 9. Yeah, okay. 9 because each one is an individual parameter. So there are 9 parameters here, and the reason is each one is one parameter. So each one is actually updated. So each and every weight is actually updated step by step. So this is one set of parameters. Again, for the next H2, let me also write H2 so that it's a bit clear. So H2 is again sigmoid of, what is H2? Okay, x1 times W12, this one I'm asking. So this is, and then plus x2 times, where is the second one? So it's here, W22. So x2 times W22, and then plus x3 times, where is the weight? W32. So this is H2, and similarly H3. So that is how the computation actually take place. Christian, actually you're right. I might have missed the bias term, but there is also a bias term. So that one, so the one over here, let me draw it. to get a full picture. So the one here also has arrows like this. So it has arrows here to this one and then this one. So you're right, the bias term also should be there. So now that we have all the bias terms at like this one again is like B1, B2 and B3. So let's add that bias term actually here now that you mentioned it. So this computation will just be plus B1 and this will just be plus B2. That's how the bias term is actually added. I hope so. What I actually want to convey is how the actual computation is actually taking place. I hope you are getting the picture of how I'm actually multiplying these values one by one and adding them up and then applying sigmoid on top of it. If it's not clear, please ask me a question. I will explain it once again because this is what neural networks is all about. This is the core part of neural networks. If it's not clear, I will explain it once more. Okay, so I think there are no questions, so obviously it is clear to everyone. So now that this happens, once this takes place, H2 is the output for this layer, but it's actually input to the next layer. So again, the same thing takes place. So now sigmoid, what is sigmoid function? Let's actually revisit the sigmoid function. So I hope I draw this correctly. Okay, so this is how the sigmoid function looks. This value, this point is 0.5. This point is 1. This is 0. So this is how the sigmoid function looks. So whatever value you have, the sigmoid function, what it actually does is it squashes the value to be between 0 and 1. You give it, let's say you input the value 10 billion. It will still squash it and bring it to be between 0 and 1. That's what the sigmoid function actually does. So it makes sure that all the activation function, the thing that actually provides the nonlinearity, that is what it does. So this is the sigmoid function. It just squashes any value between 0 and 1. Now, now that we have it, we have our outputs from this input to the first hidden layer. And now from this one, it's actually the input to the last layer, which is the output layer. So here what happens is, now the output, I'll write it here. So the output is actually W1H1 plus W2H2 plus W3H3. And as you guessed it, again, there is a sigmoid. Now, in this output, now you can see, let's say I got some value, assume that I got a value 0.8. I decided that since this value is greater than 0.5, my class is 1. So you see that from x1, x2, x3, I actually performed all the computations, used all the nonlinear functions, I used all sigmoid, I got all the weights, and then I got the class as 1. So this is 1 is the class. So that's how neural network actually passes the entire data inside and then you get the actual output. So this is how the computation takes place. Now, what I just did, what I just demonstrated, this is forward propagation. The data is propagating forward. The data is moving forward through these entire weights. So Sunil asked, is there a bias applied to the output layer? No, the bias is just so that, okay, that B is just here. That's it. Like it's finished. Once it's there here, that's all. It's this B is just meant for this one. So there's no, I mean, if you want, you can add one more one. I mean, if you want to design a neural network in that way, I mean, you can actually add that one more B over here. If you just want to make it more complex, it really depends. Okay, now that you've actually seen this neural network architecture, you are not restricted to this one. You can add thousands of nodes, more layers, more bias terms, more inputs, more. You can even have more. It doesn't necessarily need to be one here. For 3 class classifications, you can't have one node here. You will have 3 nodes. So it's really now up to you. It's like a drawing board. Figure out your architecture, whatever you want, whichever works the best. I am sure now you are getting the question. There are infinite possibilities. Which one to choose? Now you'll understand the meme. If you think about the meme, now you'll actually get why it actually takes so long to train these algorithms. Think about all those different outputs. So now let's one more thing before I answer questions. I have to mention one more thing. Now, in reality, when you're actually coding these things, when you what happens behind the libraries is, the libraries, they do not do it in this way. They don't actually sit and multiply it individually. They all do matrix multiplications. So there is something called a weight matrix. So I don't have an extra empty slide. I'll actually create it for now. Okay. I have to show this because this is also an important step. So it is the okay. Okay. So basically, you've actually seen that what you've actually seen is the regular computation. But how does the computation actually happen is, there is a weight matrix. So remember this picture. So remember that there are all these weights here, and then there's x1, x2, x3. So the way it actually gets computed, and this is a much more optimized way of actually computing these things. So instead of using a for loop to actually add these things and then keep moving them forward, a vectorized matrix multiplication takes place. So what happens is, there is a matrix. So actually, I'll draw the neural network, and then it will be clear. So what happens is, imagine that the same neural network, there's one thing here, there are 3 nodes, and there's one, and then these things are being multiplied here. So now you understand why whenever you see the picture of a neural network, you get this kind of a Spider-Man web vibe. So that's why it looks like this. So okay. So basically what happens here is, this is the input, x1, x2, x3. These are the weights, w, and then this is the hidden layer, and then this is the output layer. So now this one is actually a weight matrix. So w11, w12, w13, w21, 22, 23, and then 31, 3, 2, and then 3, 3. This is how the actual computation takes place, because it's very time consuming to write for loops and adding the whole thing. Now what happens here is, x1 is actually multiplied here. Now this is another reason why I asked you to look into matrices, because this is what I wanted to cover. For those of you who might not be from a math background, who are new to matrices, a matrix is nothing but a 2-dimensional representation of your data. So if you understood the concept of data frame, matrix is just same thing. So matrix is nothing but a 2-dimensional representation, or it can be an n-dimensional. I mean, a matrix is nothing but a way to represent your data in columns and rows. So this is how we actually represent matrices, for those of you who might not be aware of what matrices are. So basically, Hussein, you're right. So now you understand why there are 9 parameters. It's a 3x3 matrix for the weights, so there are 9 parameters. Now, what do you think will happen? How do you think I actually got this equation here? I hope I remember my okay. So the way it happens is, this okay, matrix multiplications, you can't multiply this right now. So I have to change it to it. So this is a 3x3 matrix, and this is a 3x1 matrix. So I'm going to represent this matrix as x. I'm going to represent this as w. So this entire matrix is represented by w, and this is x. And then there's a bias term. So so there's a b term. So now how this first h1 is actually computed is, this whole data is actually collected as a matrix, and then finally what's going to happen is, the output h1, let me also use capitals for vector. So h1, the actual matrix of all the h, is actually x transpose, or you can say, I mean, it's either x transpose w or w x transpose. So again, to help you understand what is transpose, I'll actually draw the diagram, then you'll actually understand it. So let me, so x transpose w plus b. Okay, this is the matrix representation of how the actual calculations happen. So computation of h inside the neural network. So what I mean by transpose is the way it gets multiplied is in matrix multiplication, there is a rule. This number here and then this number here should match. Otherwise, the matrices cannot be multiplied. So the way it happens is this x1, x2, x3, and then you have your entire matrix W, W, W. So you have this whole thing here. Three, 2, and then 3, 3. Okay, now I can actually multiply it. So the way this actually gets multiplied is x1 is multiplied with this, x2 is multiplied with this, x3 is multiplied with this. Now you're getting the exact same thing here. Like that's what happens. So I mean, maybe not the way I thought about it. I named it a bit different, but otherwise you get the idea. So this one single step happens here, and then that is the first value. So you get 3 values here. You get h1, you get h2, you get h3. I have to charge. 1 minute. Okay, there is h1, h2, and then there is h3. So now you see how each individual h is actually calculated using a matrix. So this is what actually takes place. This is how the computation actually takes place, matrix multiplications. So that's what's happened. Okay, now I guess I can take some questions. There are a bunch. Does each neuron hold a probability value? We'll actually get to that a bit later. So each neuron is not, I mean, it's not exactly a probability value, but it's just some number. The last value, the output value that you see, that can be considered a probability value because that is giving me the probability of how the output is being, whether the output is class 1 or class 0. So is it possible for one or more layer miss some nodes? I didn't understand that. Is this B to account for uncertainty when the data? So bias is some kind of a further fine tuning, maybe to account for the uncertainty. Yes, the bias is something considered like that. For input, do we have standardize the data? You don't need to. I mean, standardizing is a good option. That has nothing to do with neural networks. Standardizing the data actually is meant to scale down the data to bring the data to same scale. Okay, I guess I have answered most of the questions. One layer has 10. Yeah, okay. One important thing to mention. Okay, now I understood the question. So Jane Yang was asking, is it possible for one or more layers to miss some nodes? So basically, you don't need to have the exact same thing. I can have 100 nodes here. I can have 50 nodes here. The only thing to be careful of is these numbers should match over here. So this 3 and this 3 by 3, and then the next layer's output should match the previous layer's input. So that is something that you have to pay attention to. If I have 4 here, if I have 4, so I actually didn't consider the bias term here. If I would have considered the bias term, this would have become 1. So there would have been 1 over here. And then like you have to be, so imagine it in terms of matrix multiplications, and then you will understand how to actually adjust these neurons. If I had a matrix of 4 cross 1 and then a matrix of 3 cross 3, how do I even multiply these things? Is it even possible? It's not possible, because even if I take a transpose, nothing's going to happen. So this should be 4 by 3, and then I can take transpose and then actually multiply the matrices. So now this is the lowest level that it can get for an explanation as to how you can actually vary the number of nodes here and here. So matrix multiplication, this is why, so these are nothing but the hidden nodes. So these are nothing but the nodes. Nodes are nothing but the neurons. So these neurons, you have to vary them, and that's again another hyperparameter, the number of nodes or the neurons that you actually want in this hidden layer. So depending on the amount, the shape of the input data, you have to shape your middle layer, and then you have to shape subsequent layers. If this has 4 and you want to add one more hidden layer, you have to make sure that these two things match over here. So this one and this one should match, because that's the rule of matrix multiplication. Okay, I actually really covered a lot. I hope it's clear because these are the most important aspects of neural networks, and the rest of it is again the same thing. It's the same story. It's just you have to really understand how computations really take place inside, and then you'll understand further steps. Okay, I hope it's clear. There are no more questions. I'll move forward. Okay, now training. Okay, I've already talked about this for a lot continuously. So forward propagation is nothing but passing the data from the input to the output through the layers. So I'll again just write down the equations to complete it. So basically, a forward propagation, this is what happens. So now let me draw the neural network once more. You need to see this picture each time to actually better understand it. So, okay. Okay, now I have my neural network. I have my inputs. I have my weight matrix is here, and then I have H, and then I have output O. Okay, let's actually call that Y, so that it matches with whatever we have learned till now. Okay, so I'm going to call this Y. So now what is forward propagation? Forward propagation goes in from left to right in this direction. So this is forward propagation. Forward prop. Now, how forward prop takes place? So initially H is let's use an intermediate step actually to make it more clear. Each time I have to. Okay, so let's actually use an intermediate step called A. A is nothing but that entire matrix that you've seen. So I'm going to use the matrix notation. Remember, whenever I write capitals, I mean matrices. So X transpose, you can say X transpose W or X W transpose X. Both those are the same. I'll try to use the one that's actually most commonly used. Usually people use this notation so that whenever, if you read research papers, you'll be able to match it with it. So W transpose X, and then plus there's a bias term B. Okay. So now A took place. So we have the first step of computation. So I'll just say equation 1. Now the next step is to compute H. How is H computed? Assume that for now we are going to use the sigmoid activation functions. There are more. Sigmoid is not the only activation function. We will see sigmoid activation function actually has an issue that will lead to something called vanishing gradients, and we will see that later. So otherwise, for now, assume that the activation function, so the activation function is sigmoid. So the first step is done. I did my computations. Second step is apply the sigmoid on A, and then the last step, get the Y again. So again, computations will take place. So W transpose H, and then let me actually use an intermediate step here. So say this is A1. Now A2 is nothing but W transpose H. So that's this part. So this thing is happening here. This part is happening here. And then this H is H. Now last step, this is the equation 2. And then now what is the last step? Last step is nothing but again there's a sigmoid here. So there's an activation function. So Y is nothing but sigmoid of A2. And this one is either for now, assume that this is a binary classifier, and then you get this is the class number 1 or this is class number 0. So this is forward propagation. I am moving the data from the left to the right. So that's what happens. So this is the basic equation for forward propagation. Is this clear? If it's not, I can explain it once more. Because once this one and the next slide is covered, everything else will become very clear.
Can you explain it one more time in a short form?
Okay. So, okay. Now start here. So this is the start. and this is the end. So start here. What is the starting point? We have x, our data. So our x is nothing but, so I'll write down. So x is nothing but x1, x2, and x3. And then these weights. Now weights, W is nothing but that huge matrix that you just saw. So W and the whole thing. So the 3 by 3 matrix. So these are the weights. So W11, 1, 2, and 1, 3, and then so on. W2, 2, and then W3, 3. It's the same thing. So I'll just finish it. Okay, this is W. So now, now that you have X and then W, you just take W transpose and then you multiply. So because this is a 3 by 1 matrix, you can't multiply these two. You have to take, okay. There's no point of taking transpose of a square matrix. It's the same thing. But if it is not a square matrix, then you have to take the transpose, because if this is 3 into 4, obviously you can't multiply it, you have to take the transpose. So this W is coming from this one, and then this X is coming from here. So you multiply those two, add the bias term. So B is nothing but B1, B2, and then B3. So B is coming from here. So there's a B, so there's a 1, and then there's a B. There's a B over here. So B1, B2, B3. To be more accurate, if you have B, I need one more here because I can't multiply them. The code itself will not accept the multiplication. So now once you do, okay, there was a question about transpose. The transpose can be done anyway, depends on where you put the X value. So it just make sure that the number on the right matches the number on the left here. So these two things need to match for matrix multiplication. That is the rule. So if these two match, then you can do matrix multiplication. That's the rule. So that's why depending on where you put it. Now that you've seen it, you just plug everything into this equation, you get some value, and then sigmoid is nothing but 1 by 1 plus e power minus a. And then this a is again coming from here. So this a is this one, and then you get some value over here, some value. And then again, you have a new set of weights. This W and this W are not same. So I'll call it W1 and I'll call it W2. So this set of weights is a 3 by 3. So 3 by 3 parameters. So these are set of 9 parameters, and then these are a set of 3 parameters. So this W2 is, there are only 3 parameters. How am I saying are there 3 parameters? The reason is because if you do the matrix multiplication, so okay, so in matrix multiplication, if you take 1 cross 3 and you multiply it with 3 cross 3, the resulting matrix is, you just cut out these two things and you get 1 cross 3. So this is why you have 3 parameters here. I hope this is clear. So it's all matrix multiplications, it's all matrix calculations. So because of this matrix multiplication step, there are only 3 parameters left. So this is W1. I'll write W2 here. W2 is actually 1 cross 3. So I'll set 1, 1, 1, 2, 1, and 3, 1. So this is W2. So because of this matrix multiplication, I got W2 as this one, and then I have H. So H is from here, and then you just again take transpose, and then the next step is to apply sigmoid. Sigmoid, again, the same thing. You just have to do 1 by 1 plus e power minus a2, and then you get this value. So that's what forward propagation is all about. Okay, so people might be confused about why am I writing A1. It's just to expand on what is going on. There is no A1 anywhere in any neural network. There's no such thing as A1. I'm just splitting those steps into 2 steps. It's just that this happens in one single step. It's just sigmoid of this whole thing. And I'm just splitting that into 2 steps. That's the only reason. There is no such thing as A1. It's just to make things clear. That's all. So I hope this is clear. This is what forward propagation is all about. I'll just give you a minute to, if you want to write this down. Because next one is back propagation, and that's where the actual training takes place. So that's the one of the most ingenious algorithms ever built. And it was developed by someone. It was, you can look him up. His name is Geoffrey Hinton. He's a senior data science leader. Okay, I think by now you all have written this if you are writing it. So now back propagation. Now this is where derivatives and partial derivatives come in. After this slide, we will have a 5 minutes or 10 minutes break because there's more to cover. As I said today, I will take a lot of time to explain this because this is a very important, there are a lot of things to cover. So let's actually finish back propagation and then take a 10-minute break. So let me come. Okay, I wish there was a way to just copy paste it. Okay. Okay, now that I drew the network, so we have again same thing. We have x1, x2, x3, and then we have our weight, and then we have h, and then we have y. So now that this is the input layer, input, I'm not saying input layer, I'm just saying input, hidden layer, and then output layer. By layer, I mean wherever there are computations. There's no computation happening here. That's why I'm not saying it as layer. Now, what is backpropagation? How are the weights actually trained? So there is just, if you all remember gradient descent, the algorithm for gradient descent is there are some weights. So try to recollect gradient descent. So weights are W. These are nothing but the parameters. I'm going to use the most common notation that's used in research papers and other places. So I'm going to call W as actually theta. So theta are nothing but parameters. The same thing, I'm just changing the notation. So the gradient descent algorithm can be written like this. Theta is, how do I write this? Okay. Theta minus alpha times 2j by 2 theta. Okay. In a single step, okay, this is how the weights are actually updated using the gradient descent algorithm. I already showed this last time. So basically, theta are nothing but the parameters. So j is the loss function. So this is the loss function. Okay, I think it's better to write it as L instead of j. It's more understandable. So okay, let's say to L. So L is nothing but the loss function. So what we are actually trying to achieve is, I made some mistake. My model made some mistake. How does my model know what to correct? How do I know that? So that comes from this gradient descent algorithm. I'm going to draw the graph again. So okay, I'm going to draw it as a convex optimization problem in 2D space. In 3D, this is actually much more complicated and it's not so easy. It's not always convex. Sometimes the graph can also look something like this, and you might not find the optimal minimum always. But for now, for simplicity, just for understanding, just for recollecting gradient descent, I'll just use this example over here. So if you remember gradient descent, what it was talking about is if you plot the loss function against the parameters, you'll get a graph like this. And now what happens is, every time you take a derivative, you're taking a step in the direction of the gradient. You are actually taking a gradient and you're moving in this direction until you actually reach this optimal point where the loss is minimum, and then this is our optimal set of parameters. So your optimal set of parameters. So now you need to reach this point. How do you reach this point? You take derivatives with respect to the parameters and then subtract them from the existing ones. So let's call this theta I and theta I minus 1. So I minus 1 is nothing but the previous set of parameters. Theta I is nothing but the new set of parameters. How did you get the new set of parameters? You updated the weights by using by using this concept of gradient descent. So what you did is you had a loss function, you took the derivative with respect to the parameters. Why are you taking the derivative? And the reason is the reason you are taking the derivative is to understand the direction of the slope, to understand the answer to the question, which direction do I need to move in to actually reduce my loss. So you take the derivative. Alpha is nothing but a learning rate. You'll commonly see it as a hyperparameter. So you multiply it with alpha and you subtract it, and then you get your new weights. And then this process is repeated like 1,000 or 1,000,000,000 times to actually get the optimal set of weights. This is one half of back propagation. Now the real back propagation actually comes from the fact that it actually moves from right to left. So this is back propagation. So what happens here is, remember this forward propagation. It went from left to right. You saw all these things, all the computations took place, and let's say you predicted class 1. Answer is 0. You predicted wrong. Okay, now what's going to happen is, there is a loss function. We need to define a loss function. So the loss function, I'm going to define a loss function called binary cross entropy loss function. So I haven't really talked about binary cross entropy, but I'm going to just write it to illustrate what is binary cross entropy loss function. So assume that this is a loss function. This is one. This is called. You can actually read about it later. So basically, binary cross entropy loss function is commonly used as a loss function to model binary classification problems. So basically, what happens is, here, this is a loss function that is used to judge your output. So let's say your y is some value. So like, okay, y hat is nothing but your prediction, and then y is nothing but your ground truth, or maybe it's the reverse. I think yeah. Basically, one of them is the ground truth, and one of them is the your prediction. So let's say the ground truth is 1. Your model predicted 0.8 or something. Let's say your model predicted 0.7. So that's what's going to happen here. Like the way it's going to get the output is, it's going to, so this is y hat and this is y. It's going to input these values into this equation here. So let me write it here. So let's say your output, your prediction was 0.7 and the actual output is 1. These values are fed into this. Some loss function, something is calculated. That is finished. Now, what is this back propagation? Now, back propagation means the fact that you made some kind of error here. You didn't get 1, you went close to 1. The error should be propagated back to the weights and they should be adjusted. How they are adjusted is, you ultimately, what do you need? You actually need this, right? Ultimately, that is our goal. You need dou L by dou theta. But how do you get dou L by dou theta when there is no theta over here? Like, do you see theta over here? There is, like, theta is completely absent in this place. How do you get from this equation to this step? How do you actually come from here to here? From L, you actually need dou L by dou theta so that I can actually upgrade the weights. So I'm just saying W as theta. So there is something called chain rule of there is a chain rule in differentiation. So dou L by dou theta can actually be written as okay. So how was it? It is dou L by where is that? The initial set of parameters. Let me call this theta 1 and theta 2. So I'm going to do dou L by dou theta 2 multiplied by, and then I'm going to take dou theta 2 and then divided by I guess dou theta 1, something like this. So basically, the chain rule of probability states that the chain rule of differentiation is the fact that you can chain these partial derivatives to actually get your final result. So what I mean by chaining is, I'm actually multiplying these partial derivatives. So I have L here. L is just a function of y over here. I don't have theta. I don't have theta 1. I have L represented in the form of theta 2. So if you remember y, where did y come from? So if you look at this y is actually coming from here. So if you remember A2, what is the equation of A2? So A2 actually is a function of W2, which is in our case is a function of theta2. So that means y is actually a function of theta2. So I can actually take that derivative. So this y is nothing but this L. So L is actually a function of theta2. So that's why I can take a derivative with respect to theta2. And then after that, what I'm going to do is I'm going to move one step back. I have the partial derivatives of the loss function with respect to these parameters. What I mean by moving one step back is let's actually search for where is theta1. So theta1 is actually there here. So I'm going to take that derivative again. So sorry. Yeah. So basically I am just moving one step back at a time. So I'm just initially taking the derivative over here. This is step 1. I take the derivatives, I move one step back, and then I take one more derivative and I move one more step back until I reach the point of dou L by dou theta1. Why am I focusing so much on theta1? Because theta1 is the actual parameters that I want to vary, and every other parameter as well. So I want to keep updating every parameter. So this I, nothing but it refers to these layers. So in one step, I will update these parameters. In the next step, I will update these parameters. And then I will repeat that process. I will get a new output. I will take the partial derivatives of with respect to theta2. I will use gradient descent to subtract that, update the weights, and then I will back propagate it. What I mean by back propagation is I will use the fact that I actually have this derivative with me. I have this value with me, and then I will use that derivative to actually get to the previous step. That is the back propagation that is taking place. So the chain rule of differentiation allows us to do that. It's not so easy to understand it, but otherwise there are only two things that are happening here. Gradient descent is taking place. I need the dou L, the derivative of the loss function with respect to every step. So with respect to every parameter, I need the derivative. How do I get that derivative? In the first step, it's quite simple. I just need to take the derivative with respect to theta, because y is already a function of theta2. So I don't have any issue here. I can just simply take dou L by dou theta2 and then just subtract it from, I can just theta2 minus, and then I can get my value. But what about the previous layer? What about the previous layer? How do I get that? That's where this chain rule comes in. So imagine that I think this is much more simpler to show. So this is y. So this is theta1 x plus b, and this is x. So here the loss function takes place. So I take the derivative with respect to theta2, and then I update with this. I actually update theta2. Then to go to the previous step, this is another function. That's why I've been writing it as a. So a is a function of theta1. But how do I use the fact that I have dou L by dou theta2? So what do I do is I actually So I have to take dou. Where is it? Okay, I have to. Okay, sorry. Let me erase this. It's getting too clumsy. Okay, this will allow me to update these parameters. So the first update, I would say this is the first update. Now I also need to update these parameters. I can't leave them because all of them collectively together are called parameters. So finally, to actually get that, I have this intermediate function over here. You just use now this function will allow me to get the derivative of the loss function with respect to the initial parameters. So I need to keep taking one step back at a time using this chain rule, to keep arriving at this point. I finally need this one. To actually get that, I keep using the chain rule, and then I keep stepping one step back until I reach these parameters, until I reach this step. So that's why it's called back propagation. You're actually moving forward. You're going from X, you're multiplying X with W1, you're multiplying it with W2, and then you're getting Y. In this step, you're actually starting at Y. You're taking the derivative of the loss function with respect to the outermost parameters. So these are the outermost visible parameters. You take the derivatives, you update those weights, and then you take a step back. The meaning of taking a step back is you just multiply the partial derivatives using the chain rule to actually get the derivative of the loss function with respect to the initial parameters. And then you again use the same gradient descent. Algorithm to actually subtract dou L with dou theta, and then that's all. You actually updated theta 1. So this whole cycle, passing it and then getting back, this is one epoch. This whole cycle of passing it back and forth is like one epoch. This one is actually repeated n number of times. Now imagine I just have 3 data points and I just have 3 nodes, and this gave me 12 features. Imagine I had 100 features and I have 1000 nodes. I mean, how big is that matrix? So that's how many parameters you're actually going to get, and that's why it takes so long to train neural networks. This is a lot to digest. I hope it's slightly clear. If you want, I can show you good videos to actually understand this much better. Otherwise, this is how neural network training takes place. What are nodes, what are neurons, what are inputs, outputs, and so on. So let's actually take a break for 10 minutes and we'll continue. There are more slides to cover, but essentially we've reached the point where we've actually understood neural networks and how the computation takes place, the basic training process. The next slides will be, it's 4:30 for me. Let's again meet at 4:40. I'll stay here. You can ask any questions. Okay, let's give 1 more minute for people to come back. Okay, let me share my screen once more. Okay, so we did. I mean, there was a lot and lots of math today, but that is how neural networks are. So before moving forward, I thought I'll just summarize what we have actually learned. So let me. Okay, so this is what I guess you can hear me. Okay, so this is what we have seen. So we start with the inputs. If I just draw a small one here, I'm using the same network because it will be easier to understand. There are more complex networks as well. So let's take theta. Let's use theta for the parameters h, y, and x. So in forward propagation, they actually move forward. So the initial step here. So I'm not going to use the intermediate step right now. I'm going to just directly write it. So it's sigmoid of w. Okay, sorry, I said we'll stick to theta. Okay, theta transpose x plus b, and then finally y is nothing but again sigmoid of, so this is theta 1 theta 2 transpose h, and then finally there is a loss function. So loss is calculated. So loss is nothing but it depends on, so loss is calculated based on this y. So finally this is how forward propagation works. You just take the input, you multiply it with the parameters, and then finally you take the sigmoid. You got h. Now pass h to the next layer. So this is the hidden layer, and the same h1 I pass it to the next part, and then this is the output layer. So this is, I'll just write it down, hidden layer, and then this is the output layer. So each time I'm using sigmoid as my activation function, and then I'm just multiplying them and passing it forward. Now backpropagation will start here. So remember that y is nothing but sigmoid of theta 2 transpose h1. So how can I update theta 2? So if you go to the gradient descent, I'll say GD. So you need this one. You need the partial derivative of the loss function with respect to the corresponding parameter to actually do gradient descent. So that's what I'm going to do. So I'm going to calculate L with respect to theta 2. This is finished. I got it. Now what? Now how to get these things? L of y with respect to theta 1. How do I get this thing? So I have this. Why do I have this? Because L is nothing but it's a function of sigmoid of theta 2 transpose h1 and function of y as well. So the output. So I have this. I can clearly take the derivative. So how do I get the theta 1? I have to move back. So basically what I have to do is I have h1. So I basically I have h1. Okay, h1 is related to theta 1. I have that. L is related to theta 2. I have that. But there is no relation. There is no link between L and theta 1. I need to use the fact that I know H1 and I know these two to actually derive this one. So let's write down H1. So H1 is nothing but sigmoid of theta 1 transpose X plus B. And then what will happen if I take dou H1 by dou theta 1? So I am just going to take the derivative of this sigmoid function. So I have this. Let's put this aside. I have this with me. I can do this. But I still don't have dou L by dou theta 1. So what I can actually do here is, okay. I think I forgot. Okay. So if I just take dou, where is that? Okay. If I just take dou L, where is that? Okay. So if I just take, wait. If I take this, whatever I got here, H1 by dou theta 1, and then just multiply it with dou L by dou H1, I will get dou L by dou theta 1. But how do I even get this once more? How do I get dou L by dou H1? Again, I have to use this one from here. So basically, if you see dou L by dou theta 2, sorry, L is actually a function of H1 also. It's not just theta 2. So I can take dou L by dou H1. This chain rule of differentiation will give me this dou L by dou theta 1, and then I can use this in that equation. So finally, here I will do that GD equation here. The theta is theta minus dou L by dou theta. And then again here also, again I will do that GD equation, that gradient descent equation, theta minus dou L by dou theta. And then this completes one epoch. Both the things, forward and then backward together. So this is just to summarize the whole thing once more. Okay. So now I hope that makes back propagation a little bit clear. If you're still confused, I will send the best video that you can watch and you'll immediately understand it. But otherwise, that is forward propagation and backward propagation. All I'm trying to do is, there's only one thing that I'm trying to do. I'm just trying to get dou L by dou theta 1. How do I get that? I have to get it from the forward layers. So that's what's going on. So, okay. Now, the term deep learning actually comes from the fact that there are so many layers. So this is H1, this is H2, this is H3, and then this is the output layer. And then this is the input layer. So as you keep adding more and more hidden layers, you get a much more deeper network. You see this, how you see exponentially how the weights are actually increasing. You see each one is actually one weight. So imagine, okay, this is 1, 2, 3, 4, 5. This is 6. So there are 6 nodes here. So imagine how big this matrix is going to be. This is 1, 2, 3, 4, 5. So this is a 5 cross 1 matrix, and then this is a 6 cross 1. From 5 cross 1 to get 6 cross 1, I need a 6 cross 5 matrix. So that means 6 5s are 30. There are 30 parameters just here, and then so on, like so on. That's how you calculate the number of parameters. It's just matrix multiplications. So now I actually told you there is a problem with sigmoid activation function. So with these chain rules, each of these values is actually less than 1. Sorry. So sigmoid, if you remember, it's actually giving me a value between 0 and 1. So this value is actually less than 1. More precisely, it's actually between 0 and 1. So these values. So what happens if I multiply values that are less than 1? You will actually get even more lesser value. So if you take 0.9, multiply it with 0.9, what's the answer? 9 is 81, 0.81. It's even lesser than each one. Now take 0.8, the same thing, and multiply it with 0.8. What do you get? 0.64. It's even lesser than this. You do it once more. 0.6, 0.6. Just illustrating an example. You get even lesser value. So if you multiply numbers that are less than 1, you keep dropping continuously. You keep going down and down and down until you get to 0.00001 or something. So this is the issue with this vanishing gradients. So what happens with vanishing gradients is, imagine that it's not H1, H2, H3. Let's say it's H1, H2, H3, and there's H100 as well. From the 100th step, coming back to the first step, imagine how much the gradient has, how much this, how many, what is that, how many multiplications have taken place, how many times the chain rule has happened. So each time you move one step back, the chain, because of the chain rule, the partial derivatives get multiplied. The values, the sigmoid values which are less than 1, they actually keep decreasing. So maybe the sigmoid value started as 0.8. The value, this value, this value over here, this L, this part, maybe it started at 0.8. Now it kept decreasing. It went to 0.5. It went to 0.01. It went to 0.002. And then finally, when it come to this part, the derivative actually became 0.000005. Now, it's almost as if the weight has not even changed. It is so infinitesimally small after so many layers that the weight, the weight itself, it didn't even improve. It's okay. To provide an analogy, it's like for us to, okay, imagine that in a classroom there is no mic, and there is a there are rows of students, there are 1,000 students. The professor is speaking in the is starting near the podium and he's speaking, and there's no mic. So who can better hear the professor? Is it the person in the first bench, or is it the person in the 1,000th bench? Obviously the person in the first bench can hear it much better. By the time the professor's voice reaches to the 1,000th bench, it decreases. No, they can't hear him. That's how you can imagine vanishing gradients. So vanishing gradients means the value keeps decreasing continuously. So this gradient value, this gradient value, it keeps decreasing continuously. It's become so small that there is a minimal change in this weight, and it's almost as if the weight hasn't increased. So so Hossein asked a good point. Because of vanishing gradients, will the learning be really slow? Too many epochs. So even if, let's say, because of vanishing gradients, you use 10,000 epochs, it's still, the training is still slow, and there is a minimal update in the gradient values. So one reason is because sigmoid activation function causes the values to be between 0 and 1, and it can cause, I'm not saying don't ever use sigmoid function. It's only taking place because of the deepness of this neural network. Now, how do we overcome this? There are certain activation functions called ReLU. So it's commonly written like this. Eraser. Oh yeah, this is how it's written. So ReLU. So this ReLU activation function is one way to maybe overcome this. So the way ReLU activation function graph actually looks is, it's like this. Oh, I drew it wrong. Wait. Okay. This is the ReLU activation function. So at 0, everything before this is completely 0. Everything after this is the same. So you can have values greater than 1 as well here in this range. So overall, the ReLU activation function looks something like this. So this helps us address the vanishing gradient problem. It doesn't necessarily restrict the gradients to be between 0 and 1, but you cannot use ReLU activation function as the last layer. Can anyone tell me why? I mean, why it is actually preferred to use sigmoid activation function as the outermost layer. It's not a rule, but it is preferred. Can anyone answer why sigmoid is preferred as a last layer? Exactly, Masha answered it correctly, because we need the output to be between 0 and 1. We need the output in terms of classification. We need a sigmoid activation function, or the generalized way of sigmoid activation function is softmax. So if we have more than one class, instead of doing sigmoid, we will do something called softmax. Instead of getting 0 and 1, we will actually get probability values. So those are the different kinds of activation functions that we are going to use. So relo is one such activation function that can very well help you to use it in these layers in between, somewhere here. Similarly, max out is another kind of activation function. Batch normalization is not an activation function, it's a technique. It's a method to speed up training and overcome vanishing gradients. So batch normalization is a very practical approach to addressing this problem, to speed up the training. So when I was doing a project, we were attempting the squad. Okay, there is something called the squad challenge. It is a question answering data set. We used a very big deep neural network to do our training. When we ran the code, it actually ran for 2 days. So it took 2 days to stop. When I actually did Python main.py, it actually took 2 days to stop the program. What we did was we implemented something called batch normalization. Batch normalization is a technique. And what happened was, the moment we implemented the technique, the 2 days training time got cut down to half a day. That's a huge jump in the speed. So batch normalization, the idea of batch normalization is, every time we do some computations, we are going to normalize these weights. We are going to normalize these values here. These squares and the triangles that you see and the weights that you see. We are going to normalize them in such a way as to bring it. The distribution of those weights will now be such a way that the mean is 0 and the standard deviation is 1. This will allow the model to basically learn much faster. Because if we do not do batch normalization, what's going to happen is, it's going to chase a target that is moving forever. So whenever you do back propagation, the weights, depending on this layer, the previous layer's weights are updated. Without normalization, each time this layer tries to get updated based on these values, the value is changing drastically. The distribution of these weights, the distribution always keeps changing, because the weights are continuously updated. If the distribution continuously keeps changing, the neural network, it's very hard for the neural network to track those weights. Whenever this distribution of these weights keeps changing, the neural network chases a forever moving target. It doesn't know what are my actual weights that I need to update. In one step, let's say the weights have been updated. That's step 1. The next time I'm trying to do back propagation again, the weights are totally different because I've just updated them. If you do batch normalization, the distribution of the weights remains fixed. This problem is actually called internal covariate shift. You can search about this. So this problem is actually called internal covariate shift. So internal covariate shift means the distribution continuously keeps changing, and it's very hard for the neural network to keep track of these weights. If you do batch normalization, it makes sure that the distribution is fixed constantly, and then the training actually increases. The speed of the training actually increases. So these are some techniques to actually overcome vanishing gradients. Are there any questions here? Okay. So you will have all these. So when we actually start coding, you will realize that all these you'll actually learn so much math, so many matrix calculations, so many partial derivatives in one short 2-hour session. It's very easy to implement it in Python. All you have to do is you just have to import the packages and everything. They'll take care of everything for you. It's just that understanding these terms is a bit complicated. Batch normalization for the initialization of the weights in the weight. So batch normalization can be done at every step. So Hussein was asking if batch normalization is done initially. So batch normalization can be done here, 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 and all the places. So to get the distribution. So now this is one concept that I have to introduce right now. So bias variance trade-off. So this is not exactly related to neural networks, but it's an important concept that you need to understand. So whenever you're training some model, I think by now some of you have actually experienced this. Your model is maybe it's giving you 85% or 90% on your training set, and when you submit it to Kaggle, it's actually showing 75. It's never even crossing 80. So that's called overfitting. So your model is basically has learned everything about your training data, but it knows nothing. It is absolutely confused when something new is happening. So that's actually called overfitting. So what I mean by bias variance trade-off is, bias is basically the intrinsic assumptions made by the model. So what is linear regression? So if I have some data points like this, linear regression will try to model this and it will draw a straight line. So this is linear regression. So what is the assumption here? Can anyone tell me what is the assumption behind linear regression? There is some assumption going on here. What can anyone answer that in the chat? What is the assumption behind linear regression? There is something in that that's happening that's causing it to be a straight line. Yes, exactly. Okay, Hussein answered it correctly. So the assumption here is that my equation itself is linear. By default, I am without even looking at the data, I am assuming that my equation has to be linear. I don't even know if the data is linear or not. So basically, this is the assumption behind linear regression. Now, this model I can say is highly biased. So what I mean by highly biased is the model is biased in a way that even if I have my data points like this scattered in a circle, if I have my data points like this, it will still draw a straight line. It is so biased that it will assume anything is a straight line, anything is linear, and then it will just keep drawing straight lines. That is the bias in the model. Now, what is variance? Variance is nothing but what's exactly happening to all your code right now. Any change, slight change in the data will cause the model to throw out very wrong values, or any small change in the distribution of the values will completely throw the model off. That idea is means variance. So this is how a high variance model will look like. So imagine that again, this is the data points. This is linear regression. Now imagine the same thing. I used a neural network. Let's say I actually used a neural network and I made it so complex. That the model right now, the function that it created is something like this. So it actually perfectly predicted everything. Neural network learned a function in such a way that it actually perfectly predicted every point on this, every point on your training data. Now, if there's a new data point, it will fail to predict it. It's completely outside the scope of this neural network function. So that's what I mean by high variance. So if the model is too complex, it will try to learn every data point. If let's say there are mistakes in your own data collection, it will learn those mistakes also. So there is a very popular graph, not popular, it's not popular, it's just that this is how it is represented. So model complexity and then error. So think it goes like this. So let me just draw it with different colors. Okay. Okay, I'm not drawing some seesaw fancy curves. This is okay. So this is the bias variance curve. So basically what I mean by bias variance trade-off is your model should not be high bias or it shouldn't be too low bias. Your model shouldn't be too high in variance. It shouldn't be too low in variance. There is an ideal point that you need to see. So as the model complexity increases, the bias reduces, but the variance keeps increasing. As the model complexity reduces, so by model complexity, I mean linear regression is such a simple model. The complexity is very less. So the bias is very high. Neural networks is such a complex model, but the bias is low, but the variance is very high. What you've seen just now, decision trees, these are all examples. So low bias, high variance models. They actually can model everything. They can decision tree, this is how the boundary might look like. It will split everything perfectly. It will split the whole thing. But the problem is it learned everything. It learned too much. So underfitting means your model is not even able to predict anything in your training data. So let's say you do some training, you get some values, and on your own training data, if let's say after training, on your own training data, if the accuracy is like 50%, the model is underfitting. It did not learn anything. What about overfitting? Overfitting means it has learned everything about your data perfectly, but on the test set, it's failing completely. It's giving you 100% accuracy on your own training data, but it's actually absolutely failing and giving you 50% accuracy on your test set. So that's what this means. Overfitting means on your training data, you get very high performance. On your test, you get very low. For underfitting means on your training data itself, your performance is very low. So there is an ideal sweet spot in between. That is, you have to search. How you get that sweet spot is by training your model and then uh, uh, tuning your hyperparameters and setting your weights properly. So this is sort of slightly off track from neural networks, but this is an important concept to understand. Bias. So you will see a common diagram. You will see this is another picture to illustrate it. So if any of you have played the dart game, this is a common. So the dart board looks like this. So basically, you'll see this illustration as well in some places. So if the model has high bias, let's say this is high bias and high variance region. So high bias means basically, okay, let's say this is high bias and low variance. So when I say low variance, it means the data points are not scattered. The data points are all together, but the bias is so high that it's hitting everything in the wrong way. High bias, high variance means the data point itself is scattered completely. So basically you have to have low bias and low variance as much as possible. Like this spot here, the bias is low enough and the variance is also low enough. That means it's hitting the bullseye properly, and the variance is also not that high. So this is another popular, common illustration of this idea. That's what I said here. So overfitting is nothing but if the neural network is very complex, then it will try to learn everything in the data. It will even learn the errors in the data. So we have to somehow prevent that. And a very okay, Hussein is asking, can you explain what you mean by trade-off? By trade-off, I mean finding that ideal point where the model is not too overfit, and at the same time, it's not too complicated. So that is the trade-off. It's not some quantitative parameter that you can actually measure. It's just a qualitative idea that you need to try to get your model into. So that's the trade-off. Is just trade-off means sometimes you might have to you might be forced to have a model with high bias, but the variance is quite low. So that's what I mean by the trade-off. So sometimes you have to let go of something. Now, in neural network, in general, to avoid overfitting, there is a concept called regularization that you actually apply. I haven't covered that in this course, but regularization essentially adds weights to the weights. So it basically controls the weights. It keeps control of those weights such that they don't explode or they don't vanish, so that the overfitting, so the model doesn't overfit. So if you remember the weights from linear regression, or in case of neural networks, if you remember, our equations were something like this: beta 1 x2, beta 2 x2. So a regularization makes sure that these are a bit controlled. It makes sure that these two things don't explode. If they explode, what will happen is, when your model is predicting, it will be biased towards this higher. Let's say beta 2 is very high, is like very, very, very high than beta 1. Your model will start giving more importance to x2. To avoid that, we use something called regularization. In neural networks, one popular idea that actually worked out very well, and I will provide that research paper as well, it's worth reading. It's called dropout. So this idea, this dropout idea was very influential in, like, it was very good. This dropout tech, the idea was very good, and it worked out very well in helping us to cope with the complexity of neural networks. I can provide that paper on virtually later, but otherwise, the main idea here is to actually drop these neurons. So randomly pick whatever neurons you want and just drop them, just make them zero. That's all. That is dropout. So the way that happens is, you take this neural network. Let's take 2 and 1. So now, okay, the idea of dropout is, I am going to define a probability value. Let's say I'm going to define my probability as 0.2. With probability 0.2, I am going to drop something somewhere. Like, okay, let's say for this layer, I choose that the probability value is 0.2. What I am going to do is, randomly I'm going to pick some node somewhere, not just for any layer. I can pick some node somewhere in the hidden layers and then just completely remove it, like remove it from the network. Now what's going to happen is, the neural network is going to look like this. I'm just going to have 1 and then 1, because this is gone. It's not there anymore. Let's say it means that there is some random generator somewhere. There is some random generator that's going to give me some value. I'm going to say, if that value is greater than 0.2, drop it. Sorry, if that value is greater than 0.2, keep it. If that value is less than 0.2, drop it. That's my rule. So the idea of dropout is, I'm going to define a probability, and with that probability, I'm just going to randomly pick anything and just drop that value. By drop it, I mean completely make it zero. How you achieve that? You can do it with the weights or anything. So this, after dropout, this is what's going to happen. It's going to room. Let's say this is obviously random. So let's say I drop this one instead of that one. So I'm going to get one more neural network, and then I'm going to get some output over here. Let's say let's say another neural network is, I don't drop anything. Let's say another neural network is, I keep the original one as it is. I don't drop anything. So I have 3 different neural networks predicting, and then finally I'm going to combine the predictions and get one final class 1 or 0. Which algorithm that you all have just learned resembles this one? Can someone guess? You just learned about it. This diagram actually resembles something that you just learned in the previous weeks. A combination of different models. Which one is that? a combination of the idea of combination of different models. Ensemble learning, yes. So essentially, even decision trees is an ensemble learning model, but what I actually meant to say is the idea or the framework of ensemble learning is somehow being shown here. So this can be thought of as okay, I've already written it here. Okay, I see. I didn't see this. Okay, I don't even know if I've written this. Okay, I've just written it here. So ensemble learning, basically, the reason I'm saying it looks like ensemble learning is because if you look at it, dropout is actually randomly dropping these neurons, and each one is like a new neural network. This is like this is like model number 1. This is like model number 2. This is like model number 3. So it feels as though there's an ensemble learning taking place simultaneously. That's the idea of this dropout. So at training time, we randomly pick these nodes and then drop it. But during prediction, this is not what happens. So during prediction, you don't pick the neurons and then drop it. What we actually do is, this is training. During prediction, this is what happens. So the nodes are actually multiplied with the probability 1 minus p. So if you take the same architecture again, so the nodes are actually being multiplied by 1 minus p. This, in a way, tells me which node I have to keep, which node I have to drop. Because if probability of success is p, probability of failure is 1 minus p. So in a way, in training, when I drop a node, it's equivalent to saying that when I multiply something by 1 minus p, it's being dropped. So that's the idea that takes place in prediction. Because in prediction, we don't know which nodes to drop because you don't know the output. But here we are actually training it. So this is how dropout actually works. I will send you the paper. It's worth reading it. So we still have few more slides to cover. I already told you this is a huge topic and I'm trying to cover as much as I can today. So now we've actually covered everything about artificial neural networks. We've actually covered this whole topic. So, I mean, I think the whole thing is called artificial neural networks, but otherwise the simple dense neural networks is what we've covered now. Other types of neural networks are actually recurrent neural networks, convolutional neural networks, residual neural networks, and there are more. The more is based on what you can think of. You can think of infinite possibilities of making your own neural network architectures once I actually show you how to code them. So today I'm just going to quickly go over recurrent neural networks and convolutional neural networks. Okay, now we are going to look at very interesting stuff. So there are some certain kinds of data, they are called sequential data. So if you consider language, natural language, whatever we speak, everything depends on something that happened previously. So let's say I'm going to say the cat. So basically, let me pick some sentence. I like the pizza at that shop. It was very tasty. It was very cheesy. Consider that as a sentence. I like the pizza at that particular shop because it was very cheesy. Now, when I told, like, if you focus on what I just said, the it in that sentence actually refers to pizza. We as humans clearly know that. I like the pizza. It was very delicious. I like the pizza. It was very cheesy. The it in that word actually refers to pizza. How do we know that? We as humans have learned English and that's why we know it. But how does a machine understand it? So this dependency of the data on the previous data point is actually called sequential data. Let's take timestamp data. Weather. Okay, weather is actually a good example, or stock markets. Those are actually good examples of timestamp data. They actually depend on the previous data. So whenever you look at weather, they use all the previous history of data to actually predict the next step. So today it was actually raining, and yesterday it was raining. Day before yesterday it was raining. Previous day it was sunny. So depending on the day, I can actually forecast what is going on next. So this dependency of data on the previous data point is called sequential data. Audio signals, all these are sequential data. So Can you all think of other examples of sequential data other than language and stock markets? If you can type it in the chat. So sequential data is nothing but data that is interdependent on each other. It depends on something that happened previously. So sensor data, exactly. So all these kinds of things, they have some time dependency on, or some kind of dependency on time or something on the previous data. So recurrent neural networks are specifically been designed to address this. So can you imagine, can you wrap your head around the fact that how do we use the neural network that we have learned now to model this recurrent, to model the dependency? I mean, does it even address it? Does it even have the capability to address the dependency? Like there is no, like what's going on in the previous networks? Like if you look at the previous neural networks diagrams, what's going on here? There is, I mean, there is no scope of even having dependency on the like there is no mathematical calculation that shows me where is that interdependency happening. Recurrent neural networks have specifically been designed for that purpose. So it might look totally new, but the reason that I spent 1.5 hours today to cover, sorry, 2.5 hours today to cover those recurrent neural network calculations and the back propagation and forward propagation and all that stuff is because those exact same steps take place everywhere, even in this one. There's nothing new here. It's just the structure of the neural network has changed. So machine translation. So your Google or whatever translation system that you use, they actually use these kinds of networks on the backend. So let's take a look at this example. As an example for machine translation, this is how recurrent neural networks look like. So in English, I am Annie. In French, it is je suis Annie. So now this is how machine translation system works, and this is how the interdependency actually works. So who am I talking about here? This Annie is my name. So this I actually refers to Annie. So that interdependency is being captured in this neural network architecture. So what's happening here is each time whenever it gets, so initially the output is, sorry, the input is being fed in this way. It's just been rotated horizontally, but the input is being fed in this way. Now, once the word I is fed into this, there are some calculations that take place. Some sigma, some kind of calculation, plus minus matrix multiplication, something is taken inside, and then the output is je. And then finally this output will go here. And then it will get this new word because I said je, I'm going to predict the next one. And then again, it's going to go to the next one. So that's overall machine translation. This is what happens. So in machine translation, basically every previous word is being fed, the output of the previous one is being fed to the next one, and the dependency is being, each time the memory is being recorded. So each time the memory or the dependency is being recorded and it is being moved forward. So this is how recurrent neural networks actually work. Now, there is one thing that you will notice here. If anyone can guess it, you can type it in the chat. So there is one big difference between recurrent neural networks and regular neural networks, other than the fact that it's capturing the dependency. So in the regular neural networks, you've seen that there's an entire huge weight matrix. So there were so many W's over here in the previous neural networks. Here, there is a shared parameters. That's the biggest difference between regular neural networks and recurrent neural networks. So if you see everywhere, I've actually written WI, 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 and then WJ, WJ, WJ. It's the same thing. These all are actually same. These are the shared parameters. So this is one huge difference between neural networks and regular neural networks and recurrent. These are actually shared. Why are they shared? Because this shared parameter actually knows that the word Annie is actually referring to I. It has that data. It has learned the fact that these two are related based on these shared parameters. That's the beauty of this recurrent neural networks. It captures the dependency. So everything else, back propagation, forward propagation, equations, the whole thing is exactly the same. the equation for this is it's x0 times wi plus x1 times wj, and then there's a sigmoid, maybe there's a sigmoid inside this, and this is y. It's the same thing, it's exact same thing, and then wi is again fed into this, and then it's wi times something inside x2 times wj, and then y2, and then finally you keep moving forward. So that's how recurrent neural networks looks, and that's how it actually works. So I mean, I left this page just for that particular calculation. So if you see here, let me call this h1, h2, h3. So the first step, we start here. So this x0 is actually random. This is time step 1, time step 2, time step 3. There should be a time step 0. We don't know what that is. We don't have the data for it. So it's either random or it is completely zeros. It's all zeros. So now let's actually do forward propagation. We already spent so much time on forward propagation. So let's just say h1, some activate. I'm going to say fn to keep it general. I'm not going to keep using sigmoid. So function of x0 wi plus x1 wj plus maybe you can add a bias term. Then next step is h2 equals, we already have h1. So function of h1 times wi plus x2 times wj plus some other. This is, let's say, beta 1. This is beta 2. And so on. It keeps going on. And then y1 is nothing but some other g, some other function g of this h1. And then y2 is again nothing but again some other function g of h2. So that's how recurrent neural networks, the processing takes place. It's the exact same thing. Again, back propagation is again, you have some loss function L, you take dou L by dou wi, and then you multiply it, and then you get dou L by dou wi minus 1 into dou h by dou and something. It keeps like the same exact story. Like it's the whole same thing, just that. So now this is the example of recurrent neural networks. Now there is a problem of vanishing gradients. Are you able to understand why vanishing gradient? How can vanishing gradients come here? If let's say the sentence is 100 words, now imagine back propagation taking place across those 100 different units. These different things, they are called units. So you can say this is an RNN unit. So if there is h1, h2, h3, and there's h100, by the time the gradients come back, it's going to be very less again. So this is again the vanishing gradient problem. So to address that, a new algorithm specifically designed for addressing vanishing gradients in recurrent neural networks was invented, and it's called long short-term memory networks. This exact image and this equation, I've actually taken it from a very good blog. I've provided the link to that blog in the notes. You can look at that, but otherwise, that blog has a good explanation of what long short-term memory networks does. So don't, for now, ignore this. No need to worry about such complicated equations. Focus here. So this is a single LSTM cell. So okay, this is a single LSTM unit. And then what happens here is there is something called a cell state inside an LSTM unit. So if you see this HT, this HT is same as this H1. So because of this vanishing gradient, because of all these partial derivative multiplications and so and so, what they thought of doing this is they kept this single line. If you see this line, this actually takes the input and just carries it forward. Nothing is happening. If you just forget this entire thing that's happening inside, the output is just being taken and it's just being passed forward. There is no computation at all. Nothing is happening. That is what we mean by memory. So each LSTM unit is storing some memory and it's taking it forward. Now, if you have some sentence, the cats like playing, or the cat was playing. So in this sentence, cats is plural here and cat is singular here. Now the words later that come up here are dependent on whether it's plural or singular. So if this is only 4 words, if you have 100 words and some word in the last part actually depends on somewhere in the previous, some word in the beginning, it needs to remember that fact. We as humans can remember it. How does a machine remember it? That's the entire idea behind LSTM. So these things that you see here, so these ones, so these things that you see here, these are called gates. So these ones, RT, where is that? Yeah, these things. So HT, sorry, not that one, sorry. So if you see these equations, these ones, so Z, this one, these things, these are all gates. The way LSTM works is, what this is doing here is, there is something called update gate, forget gate, and then output gate. Now I won't go into the math because we are slightly on time, running a bit out of time, but the way LSTM works is, it has these gates. The function of these gates is to do exactly that. The forget gate, what forget gate does is, it registers information that the model needs to forget in the future. It has the info, it stores the information that it needs to know in order to know what to forget. And update gate, it has the information that it informs the model of what to update. And then output gate actually combines finally forget gate and update gate. So that's what happens here in these 2 steps. So the X mark here, these things, this is where all the gate computations takes place. So the input is coming like a train. Now this gate, it tells the model, okay, you need to forget the fact that this was singular or this was plural, and it gets registered in this part. And then you need to update the fact that when you want to predict some word here, update the fact that cat is actually singular or plural, and then it starts updating it. And then the output, so these 2 are different things. So now the model actually stored 2 sets of pieces. So one thing that it stored is, what do I forget? Another thing that is stored is, what do I actually update? These 2 are different pieces of information. Finally, it needs to be fed into this train that keeps coming here. So this data, this is like a data flow. So the data is flowing from left to right. As it keeps flowing, it needs to get information on what to forget and what to update. That's what happens in these gates. And then the resulting output is either it remembers some information, or it forgets some information, or it just carries it forward. And this is the main idea behind long short-term memory networks. The memory actually comes from the gates. So this is a very, very quick and high-level intro to LSTMs. I will share the blog that actually explains it in a much more depth, but I just wanted to introduce LSTMs here. So this is such a unique and such a nice, such a very advanced concept. Can you all guess when this was? I think this has been recently been picking up a lot of pace and getting a lot of traction in the data science industry. So can you all guess when this was actually invented, this algorithm? Okay, yeah, it is a pretty old one actually. It's been there since 1990s, but recently only it started getting traction, and the answer is GPUs. So this is the last part. I guess all your brains are a bit heated up today with all this information. This is the last and final slide that we have. After this, we will actually dive into the code. So I'm sure all of you are a bit tired now. but try to bear with me. This is the last slide. So convolutional neural networks. So we have seen neural networks. They are universal function approximators. They help us to get certain, they help us getting certain like prediction, like classification, regression tasks. They learn those functions and they predict some outputs. Then we have seen recurrent neural networks. Sequential data or variable data. Basically, if the like it's English sentences or it can be anything. Like the data is variable. Like it's not necessarily fixed. Like in the first neural network architecture, we have seen. I'll draw it here. So in the first neural network architecture, we have this fixed. Like if you understood this architecture now, this is actually fixed. Like you can't change this. Like I mean, you can't change it dynamically. You can change it before training, before feeding it to the model, but you can't change it dynamically. Recurrent neural networks helped us overcome that fact. So these cells can actually change dynamically depending on your input. So it can dynamically change. Now let's come to images. So how does an image actually look? So if this is an image of some mountain, and then there's a sunset happening here, and then there's some river flowing somewhere. So if this is an image, now this image is actually made up of small pixels. So tiny pixels. This actually image is made up of these different pixel values. So what kind of neural network do I even have to use to understand images? So one straightforward answer is, let's say this image is 800 by 600. So I can just use a simple neural network and create, how much is this? 8 6 are 48. So 48 0 0 0 0. Okay, so it's 480,000. So it's not bad, right? I can create a neural network that has 480,000 inputs and then create my neural network. Now this is not an ideal solution, because 480,000 input values representing the image, each one representing the pixel, is going to take so long to train, and there are so many billions of parameters that it might not give it might give you a good answer, but it will take so long to train that there are much more better efficient ways to actually solve this problem. One such architecture that was developed to, and which is popularly being used for doing computer vision and image processing, is called convolutional neural networks. So I'm going to after this I'm going to show you one last image that might actually blow your mind, but try to just focus. So the idea of convolutional neural networks comes from this mathematical operation of convolution. So the exact equation is actually xt w I minus t. So this is how convolution takes place. It's the integral. Integral is nothing but the sum of values. So convolution is nothing but you have some function x, you have another function w, you're just multiplying them and taking the integral. For discrete values, this is what convolution, this is how convolution takes place. How does convolution actually takes place? So inside the neural network, this is the computation that happens. So imagine that this is your image. This is your single image. Imagine that the baby Yoda that we have seen in the first week is sitting somewhere here. Now, how big is this image? So each one, imagine it's a pixel value. 2, 3, 4, 1, 2, 3, 4. So it is a 4 by 4 image. So the way convolution takes place is we have something called kernels. So we have filters. So let's say I have a kernel. Just imagine, for the sake of examples, I have a kernel that's 2 by 2. I'm calling it a kernel or filter. Now what happens in convolution is, this kernel is taken throughout this entire image. So this kernel is first placed here, and then let's say the kernel value is 1101. Now this kernel 1101, it multiplies every value and it then generates a new feature. So what happens here is, imagine that the pixel value behind was 2. This pixel value behind in the bigger square was 3. this is 1 and this is 0. This is what convolution, this is how convolution takes place. This 1 is multiplied with the 2, 1 is multiplied with 3, 0 is multiplied with 1, 0 is multiplied with 1, and they are all added up. So when you add all this up, what happens? So it's 2 plus 3, 5. So basically I have a new feature, that's the value of that feature is 5. Then this kernel is slided forward. So the kernel moves from here to here. The weights are the same. I didn't change the weights. The weights are still 1, 1, 0, 1. And then pixel values changed. Now the pixel value is there's 3, there's 0. Let's say this is 6 and this is 9. So now again, 3 times 1 is 3, 6 times 1 is 6, 0, and then there's 9. So 9 plus 3, 12 plus 6, 18. So the next value I got is 18. And then the kernel is again slided forward. So now it's here, the kernel is here. I do some computation, I get some value, something, let's say it's 21. Now the kernel is taken here. It's moved, it's slid over here, and then again those computations takes place. Let's say the value I got is 8. And then the kernel moves here. So try to follow along what I'm saying. So the kernel, if you follow my direction, the kernel is actually being moved along this image. And then some new values are being generated here. Now this is my first set of features. After I applied this kernel on this image, I actually got something new. Now this is my new feature. Now again, in this way, I'm going to use hundreds of different kernels. Like let's say I'm going to take one more 2x2 kernel, and this time the values are 0, 0, 1, 0. Again, I'm going to use this kernel and move it around this image and get another feature map. So these are called feature maps, these things. So in this way, I'm going to create different feature maps, and I'm going to stack them. And finally, I'm going to keep moving. I'm going to keep doing this. I'm going to keep doing this. And in the end, finally, what I'm going to do is I'm going to flatten this whole thing out. Imagine that my last feature map was something like this: 1, 2, 18, 21, 3, 4. Imagine that after all these steps, my last feature map was like this. I'm going to flatten this out. And then it's the same story. I'm going to use my very old neural network and then get my prediction as 1 or 0. So this is how convolutional neural networks actually works. I've taken this image from a research paper. I've actually provided that link below. So this is what happens. So you take the image is made up of different pixel values. So small boxes, it's not even visible to the eye. It's actually visible here. You see these small squares, these are actually the pixel values. So the image is made up of such different square values. Now, I have used a 5x5 convolution. It means this kernel that I've just showed you is 5x5. So what happens here is I chose a 5x5. I chose a 5x5 filter. I moved it throughout this image, and then I generated this feature map. In the same way, I've chosen different kinds of 5x5 filters, and then I've just generated 5 feature maps. And then what I did here is these steps, these individual steps, what happens here is I apply more different kinds of functions. So there are different kinds of functions called pooling. What happens is, if you understood what happened here, essentially, can someone tell me now where are the weights here in this neural network? Which matrix here represents the weights? What will actually be learned here? Can anyone guess? What is actually going to be learned here? Where is the learning going to happen? So where are the weights here? I haven't talked about weights. All I'm talking about is kernels, filters, and the convolution. You can throw any guess you want. Okay, so you are close, but the answer is this. This is the weight. These are the weights here. So this filter here, this is what is actually learned by the algorithm. So the convolutional neural network actually learns to model those kernels. That's the weights here. So this is the W that actually the model learns. So each time this is one weight matrix. This is another weight matrix W3. This is another weight matrix W4. Another. So these are not the weight matrices. These are the outputs of the weight matrices. So output of convolution, each one. Now, after you do that, one common step is, let's say you got this feature map. You got, after you did the convolution, you got some feature map. The next step, one common step to do is called pooling. So what pooling does is, let's say this is your output. After you did the first convolution step, you got some output here. Now pooling is another filter. What it actually does is, it takes this block and then it does something here. Let's say the pooling is actually called max pooling. That means this feature map, pooling, what it does is, it goes over this feature map and it selects the max value. Then it moves here, it selects the max value. It moves here, again it selects the max. It moves here, and then it moves here. Each time it selects the maximum value, and this time I got 4 values. So max 1, max 2, max 3, and max 4. So that is what this intermediate step actually does. So it is the same convolution step, but this time there's no convolution. It's just selecting the maximum value. You can have min pooling, you can have average pooling, you can do anything. Again, apply those kernels, you get some output, and then finally this is where our old neural network comes back. So you flatten the previous filter, I mean the previous output, and then feed it to a neural network. This is actually commonly referred to as feed forward neural network. So this part. So this is the CNN, and then this is the feed forward neural network. And then finally you predict the class 1 or 0. Okay, I think I have covered neural networks in 2 hours and 50 minutes. Okay. How do you decide which filters to use in the first place? Okay, this is a hyperparameter. So I chose 5 by 5. I could have chosen 3 by 3. I could have chosen 2 by 2, or I can choose a combination of everything. There are complex convolutional neural network architectures that are being built, and this is what happens on the back end. So I can choose different kinds of filters. I can choose 3 by 3, I can choose 5 by 5, 2 by 2, all at the same time, and then stack them up together, just like I have stacked this. So I can stack up 3 by 3 filters as well, and then I would get another set of stack. All these things I would again pool together and then feed them forward. So I guess there's only 10 minutes left, but if anyone has any questions, you can ask me. Otherwise, I can show you how simple it is to actually code neural networks after showing you such a huge explanation. So if anyone has any questions, I will wait. Otherwise, in 10 minutes, I will show you. Yeah, so, okay, Eric is asking, why did I choose 5 by 5 or 3 by 3? So honest reason is, there is no logic to choosing that. Okay, now this is really getting into image processing and computer vision. It really depends on what kind of features you want to capture. So this is called a feature extractor. So if you can imagine in an analogous as an analogy, what's happening here is the features of this image. So if you see, okay, let's actually look at this digit 3. So the features of this, okay, how do you know that it's 3? Because the shape is like this. That's why you know this number is 3. Now, how do I know which filter to use? That's like a computer vision problem. So let's say I use a 1 by 1 filter. Is it any use to me to capture this area? I don't know anything about this. Like, there's no point of capturing this. But how do I capture this shape over here? Is 5 by 5 good enough to capture this, or is 8 by 8 good enough to capture this? So that's how you start your thinking into choosing the filters. It's a computer vision problem. I hope that answers your question. Okay, so let me share my screen, and for the last 10 minutes, let me quickly go over the code example. If your notebooks are open. So yeah, so basically this is what we have today for the week 5 notebook. So I straight away took the code directly from the last week. So I'm not going to go over the data set once more. There are two popular, there are so many frameworks to actually do deep learning. I am sticking to one such framework that's called Keras. So if you just visit keras.io, this is a popular, very simple to understand and easy to use deep learning framework that's built on built for using it with Python. So basically, I would suggest visit this website and try to understand the API very well. There are so many terms to actually understand how to use it. So everything that you just learned, layers, models, neurons, hidden layers, all your weights, regularizers, dropout, convolutional layers, you'll see everything that's been coded here. That's why I took almost 3 hours to actually explain neural networks so deeply, because to be able to use these packages, you need to understand what's going on. So let's actually see how to use Keras and how simple it is to design a neural network. Let me actually show you using, I'll show it to you in a different way so that it's easier to understand this one. So let me go back to okay, I am sharing my screen now. Okay. So I just wanted to show it to you in this way so that it's easy to understand. Okay, so if you can see this, okay, if you can see this neural network on the side, so are you able to see the screen? Okay, so I'm going to assume that yes. So this is how Keras actually looks. So basically, I did the same thing. I just did again the same feature extraction. I just split my data. Now, how Keras actually allows us to do deep learning is the most simplest. Okay, this is not the only thing. There are multiple different ways to actually code neural networks using Keras, but I've chosen the simplest one to actually understand it easily. So Keras defines something called sequential. Sequential is a class defined by Keras that allows us to code this part. So this exact architecture is being represented here. Now, when I say sequential, I'm actually initializing a class, and my object, I'm just calling my object model underscore simple. Now, how do I add layers? So it's just as simple as saying dot add, and then when I say dense, I mean this one. So whatever you see on the left, the 3 nodes, that's called a dense network. So when I say dot add dense, I mean this one. Now, what is this 12 and what is this 7? So this input dimension 7 actually refers to x1, x2, x3. So in this case, I said 7. Why did I say 7? Because if you look at my xtrain has 7 columns. So this is x1, x2, x3, x4, 5, 6, 7. So this 7 input dimension 7 actually talks about these x values, and then this 12 is actually talking about the hidden layer. So this 12 actually means this h, so the hidden layer. So I am saying the input is 7 nodes, and then as the first layer I want 12 neurons. Activation, I'm setting it as ReLU. Next, I want to add one more layer. Now remember, now again I'm saying the next layer should be 12. I don't care what is the output of this one. That's the simplicity that Keras provides. There is another, so I am saying the first hidden layer should be 12 nodes, second hidden layer should be 12 nodes, last hidden layer, because this is a classification task, I chose activation as sigmoid, and then I chose 1. So 1 means the last one. Now all you need to do is run this. If you remember, I said I would use the loss function as cross entropy. So that's what I defined here. I said loss binary cross entropy. So all these things, these are actually available in this Keras website. So if you check the optimization or the losses, if you see losses, you see binary cross entropy loss. So that's what I've defined here. I've exactly used the same thing. So binary cross entropy loss, and then optimizer, I've chosen Adam optimizer. I haven't talked about Adam optimizer because, okay, I haven't talked about a few things because this is such a huge concept that it's not possible to cover it so easily. But the fact that I'm introducing it to you means that it's good for you to actually read about them. And then metrics, I have decided that I will use accuracy as my metric. So after you define your model, you add your layers, you compile your model. Now you just say dot fit. And I chose 150 epochs and I chose batch size as 10. So I'm going to feed 10 at once. So you see the accuracy, it's actually training, and accuracy is somewhere stuck at 82. So after 150 epochs, it will start and you just do dot predict. It's the same exact thing. So now this is how you use Keras. There is one more popular, I haven't covered it today because I'm sure all our brains would have exploded today. I haven't covered this because PyTorch is one more very popularly used deep learning framework. I have personally used both of them, and this is not so straightforward, but still it is a very powerful package. I'm not exactly sure, but I think Facebook has developed this one. PyTorch is a very popular package, and if you actually go to the docs, so if you check the docs, I'll actually quickly show it to you so that we can end today's session. So where is okay? So okay. Now that you understood how simple it is to construct neural networks using Keras, all I did was I just added these layers. So I just added add, and I did sequential, and I just did dot fit, and then you do dot predict. If you have 10 inputs in XTrain, you have to put this as 10. Whatever, this is the input dimension. So this is the number of features, number of columns that you have. So that is Keras. All you had to do was dot fit, and then you do dot predict, you'll get your answers. But when you use PyTorch, let me actually show you. So everything is there in their documentation. So when you decide to use PyTorch, wanted to show you one simple example. Okay, you can already see that PyTorch is very complicated. So okay, this is how a PyTorch neural network model is actually defined. You need to actually write this whole code by yourself before you even decide to create a neural network. It's not as simple as saying dot add. You actually have to write this code where you have to define each individual layer, and you have to define the forward propagation layer, and then in training you actually have to make prediction, get the loss, do the back propagation step that's actually happening here, the backward step, and then make a step in the direction of the gradient, and then keep moving forward. This is how PyTorch actually works. So depending on which framework you're comfortable with, you can choose either one. Both of them do the same exact thing. But yeah, so I guess we are exactly on time, and I covered everything that I wanted to cover today. Do you have any questions? We have 1 more minute left. Okay. Okay. So before you all leave, I have to inform you something. So regarding phase 2. So regarding phase 2, it is now next week. Like, okay, this is the end of our entire course. This is the end of your 5-week machine learning bootcamp. Basically, phase 2 is next week on week 6. We are going to talk about the individual projects that you're actually going to do. So next week, the mentors will come in and they'll show you all the different projects that they have for you, and then you can choose whichever one you want. And then we won't have a week 5 assignment. Instead, we will have the final test. Like we'll just have one final test that I'll send out by tomorrow night, Then we'll give you 1 week or 1 week and 2 days to actually do the assignment. And then depending on that assignment, and that assignment is not the only criteria for your selection. The assignment and then the your participation in the class, the way that you're interacting with us, everything is actually considered, and not just the assignment, to actually decide to move you into phase 2. I guess that's what I wanted to say. Zoe, if you want to add, or Rohan, if you guys have something else to add.
Hi, Ani, I have a question. So in that today's class, you mentioned that the input dimension is 7, but actually after dropping the features in DF train, we have 10 input dimension. But when you are selecting like input dimension equals to 7, is it choosing 7 randomly out of 10?
No,
or?
I chose 7. Like I specifically chose 7 as my input, and then I'm saying it is 7. So that neural network doesn't do anything. You need to feed it on your own. So the neural network doesn't automatically choose 7. I actually chose 7, and then that's why I entered in the input as 7.
Yeah, I mean, choosing 7 means out of 10 you are choosing 7.
I'm choosing the best 7 that I thought will work.
Yeah, so what are those? How can I understand that out of 10, which 7 you are choosing? There is nothing to quantify, right? Like for example, P class, age, SBI, SP, perch.
No, that's up to us, right? Those are the features that I want to input. Like when you print Xtrain, like what I'm saying is that's my choice. I'm saying, like, if you just type Xtrain, that's actually my personal choice.
Sure. Okay.
Yeah, that you can have 20 features also if you can create them.
Okay. Okay, got it.
Okay. Okay. I think we have to stop. Rest of the questions you can direct them on Slack. Thank you all for attending, and have a great evening ahead.